One of the things that makes problem 18 snailfish so interesting is just how many different approaches there are to it. For example, you could do this using regular expressions actually. Another way is you could implement a custom tree class to perform the operations specified here, which is what I did originally, but it's pretty slow in terms of writing it. So today I'll be going over how you can solve this using just recursive functions and normal lists in both Python and JavaScript. So first let's look at the specification. So we have a snailfish number is a pair, and the pair either contains another pair within it or just a plain number. And those pairs can of course contain pairs themselves or numbers, and this can nest however deeply they want. And the reduction process happens like so. You must repeatedly do the first action in this list that applies to the number. So what that means is if explosion is valid, you must do explosion first. Only if explosion can't happen anymore do you then split. And if splitting causes another explosion to happen, you would do an explosion before you would do splits again. So if a pair is nested inside 4 pairs, that is, it has a depth of greater than 4, then the leftmost such pair explodes. And if nothing can explode anymore, then if any number is greater than or equal to 10, then the leftmost such number will split. So when a pair explodes, it becomes a 0, and its left number gets added to the closest number to its left. And this is where things get a bit tricky, because with the nesting structure, how do we know exactly how to get to that node? And the right number gets added to the right neighbor. And of course, if either of these neighbors don't exist, the number just gets lost. And at the end, the pair itself becomes a 0. And to split a number, we replace it with a pair, the left side containing the half rounded down and the right side containing half rounded up. So the way we can do this neighbor thing is every time we recurse into a pair to see if we can split it, we keep track of which pair is on the left and what is on the right. And then to get the left neighbor, we just look at the pair immediately to its left and get the rightmost element of that pair. To make things a bit easier, I'm actually going to pre-process the input a bit. So first let me grab the test data. So for a line in open0, what I'm going to do is, instead of just representing as a list, I'm going to replace each regular number with a list of length 1. The reason this is useful is because that way when we pass this list into a function, we're able to mutate the list to directly modify the original reference. Whereas if you just had a plain number, you wouldn't be able to do that. So let's let m be the list of shellfish numbers originally. Then what we're going to do is we'll define a recursive function convert, which will just take a regular list like this and replace each regular number with a pair. So basically if x is an integer, then we'll just wrap it up, and otherwise we'll just convert each element. And so then we'll just do m.append convert eval line. And so that gives us basically the same thing, but we've wrapped each number, so now it's a list, so we can pass the reference around and mutate it. So we're going to need 2 functions. First we're going to need the explode, and we're also going to need the split. So we're going to make our explode function take 4 arguments, because we want it to be recursive. The first one will be the value we're trying to explode. Then we'll have the neighbor to its left. So how this works is every time we descend during our recursive explode, if we go to the left neighbor, then we set the right neighbor to the other value in the pair, and similarly if we descend to the right side, the left neighbor becomes the left side. Hopefully a diagram will make this a bit clearer, so let me just draw this out. So using the example they give here, we have this pair here. So on the left side we have that, and on the right side we have 4. So the right side is 4, and then on the left side we have another pair whose right side is 3, and whose left side is another pair. And the right side of that pair is 2, The left side of that pair is another pair with the right side being 1, and then the left side is a pair containing 9 and 8. So initially, when we start at the top here, the left neighbor does not exist and the right neighbor does not exist. Now this isn't technically true because the left neighbor would be this and the right neighbor this, except since this isn't a value, that doesn't matter. So if we were to descend to the left side, then our left neighbor would still be nothing, but our right neighbor would become the right side. And similarly, if we descend to the right side, the left neighbor becomes the left side. So let's say we descend onto this side, so now this is our right neighbor. Then if we descend to the right, our right neighbor stays the same. And notice that this ordering is correct. And the left neighbor would become this, which is also correct. However, we continue to descend to the left, which sets our right neighbor to this, and then to the left again, which sets our right neighbor to this. And finally, when we get here, our left neighbor has remained empty this whole time, and our right neighbor is this node here. And so when we destroy this pair, then it will work out. So we're going to keep left, which is initially none, right, which is initially none, and the depth, which is initially 0. So if x is a single number, so the length of x is equal to 1, then we return false. So we're going to make our recursive function return false if no splits happen in this branch, and true if a split did happen. And this lets us shortcut to only explode the leftmost pair once, and it also helps us in our reduce function later to identify which action happened. Otherwise, if the depth is at least 4, and the left and right numbers in the pair are both single numbers, so the length of the left side is equal to the length of the right side is equal to 1, then we want to explode this pair. To explode the pair, we first have to add its elements to the side parts. So we're going to use two utility functions that I'll define later. So to add the left side to the left, the immediate left neighbor, we'll call a function called add right. Now why is it called add right? Because the left neighbor is the rightmost element of the left block. Remember that the left block is potentially arbitrarily large. All we know is that the rightmost neighbor of it is directly adjacent to our current pair. So we'll add right to the left neighbor, and the value that we're adding is the left side of the pair. Likewise, we'll add to the leftmost value of the right neighbor the value of the right side of the pair. And finally, we will replace this pair with a 0 by doing this. In case you are not aware what this syntax is, if we were to just do this, s equals 0, this would set the variable s in our local scope. Oh, sorry, I meant to say x here. This would set the value of x in our local scope, and it would not affect the actual object itself here. However, by doing this, what we're saying is assign to x itself, so mutate x, and replace the slice from the beginning to the end with 0. So this sets the reference itself of the object list x to just be a singleton list containing 0, which in our syntax here is just the number 0. And then we'll return true because an explosion did happen. And now otherwise, we will return explode something or explode something. So this is where the shortcutting syntax comes in handy. If the left side returns true, the OR here will shortcut and say true, which tells this function here that an explosion already happened, and so the right side gets skipped. So we'll first descend on the left because we need to explode the leftmost neighbor, the leftmost pair. So we're going to descend to the left side, which is x0. The left neighbor remains the same. The right neighbor becomes the other side, and the depth increases by 1. Similarly, we descend to the right side. The left neighbor becomes the other side. The right neighbor remains the same, and the depth increases by 1. So now let's define those two utility functions. So recall that add left adds to the leftmost value of x. So if the length of x is equal to 1, then we just modify the value itself, and otherwise we will just add to the left side of x. So basically we'll recursively seek for the leftmost point in x. One extra condition we have to consider is that L and R here could be none, which is intended behavior because the exploding pair might not have neighbors. And so if x is none, then we just return. And we do pretty much the same thing for add right. If x is none, we just skip, and otherwise, if it's a single number, we mutate it, and otherwise, we recursively go towards the right side. So that's the explode function done. Now let's do the split function. So here what we need to do is, if the length of x is equal to 1, that means we found a single number. So if the single number is greater than or equal to 10, then we will replace it with a pair. And this is again where having a list reference comes in handy, because now we can again do the slice thing. And so the left side will be a single number containing x divided by 2 rounded down. Now remember that we have to wrap this into a singleton list according to our syntax. And the right side is just the ceiling division. And in case you haven't seen this syntax before, the way this works is when we negate it, then floor dividing it will make it ceiling on the other side, basically. So, for example, the floor of 2.5 is 2, but the ceiling, the floor of negative 2.5 is negative 3. And so, since flooring on the negative side moves it away from 0, when we negate it again, it pushes it upwards, and so it becomes ceiling. You could also just do x0 minus x0 over 2, for example. And then we return true because a split has happened. And otherwise, if this is a single number but it's not large enough, we just return false because no split has happened. And otherwise, we will just try to split the left side first. If that doesn't work, we will split the right side. So the split function is, of course, a lot simpler. And so now let's define our reduce function. So reduce is going to take some value x and just completely reduce it down. This is actually pretty easy to do now that we have everything done. We just do this. So we repeatedly call this here, so we'll try to explode, and if no explosions can happen, it will try to split. And so long as one of those happens, it will keep repeating over and over again. And when neither an explosion nor a split happens, the loop just automatically ends. Okay, so now let's move down all the way to the bottom here. So the way this works is we basically need to cumulatively add up all of these values, reducing at each step along the way. And so we'll begin an accumulator called A, which is initially just the first value of our list of values here. And then for each subsequent value, we will add it. So addition for snailfish numbers, we just pair the left side with the right side, so that's equivalent to a plus equals k in snailfish language. And then we just call reduce on a, remembering that it mutates the value itself. And so this should, in theory, give us our final value for a. And so now all we need to do is figure the output format, which is the magnitude of the sum. So if it's a pair, we take 3 times the left element's magnitude plus twice the right element's magnitude, and a normal number's magnitude is just itself. So we define a recursive magnitude function. If it's a single number, we just return it, and otherwise we return thrice the magnitude of the left element and twice the magnitude of the right element. And there we have it. 4,140 is our correct sample answer. And let's just try on our full input for good measure. And we should get 4,017, which is correct. And part 2 is a pretty simple modification. Basically, what's the largest magnitude you can get from adding 2 numbers? So we'll just do it like this. The maximum sum is going to start out at negative infinity. And so we will just do a double loop through m. And doing a index loop allows us to make sure that we don't run into the same element twice. I don't think there are duplicates here, but just in case there are, we want to use index checks to make sure we account for that. So if they're the same, we just skip it. And otherwise, we'll say k is equal to mi, mj, reduce k, and ms is equal to max of ms and the magnitude of k. Now, before I run this, I can already tell you this is 100% not going to work correctly. And the simple reason for that is that, remember that reduce mutates, and when we create a list here, these haven't been copied, so we're just mutating. So we could define our own recursive copy function because the list goes as deep as, like potentially very deep, and so we'd have to recursively copy, or we can just import it. And so this is a useful thing to know, because if you do want to do mutation, which in a lot of problems is a lot easier than trying to do it statelessly, then you should have deep copy remembered. So you can just say k is equal to deep copy of this pair, and so that creates a new reference, and we can reduce it and mutate it without affecting the other values. And so we get our puzzle answer of 4,583. And it runs in just over 2.5 seconds, which is pretty decent. And so the general idea here can be copied over to pretty much any language that has mutable lists and the ability to pass list references into functions and mutate them like we've done here. In case your language doesn't have a slice syntax like this, that's not a problem. You can just say, like, since x is length 2, you can do x.pop to remove the other element, and then x0 is equal to 0. So that would work as well. And down here you can just do x0 is equal to x0 divided by 2. Sorry, we need to store the value of x first. And then x.push to create the new value. V negative v divided by 2. And so if your language doesn't have that slice syntax, that's not a problem. You can just work around it like so. So hopefully this helped you out, and the general tips of using recursion with mutation to allow you to, like, recursion with mutation is actually a pretty powerful construction here. In fact, it's, in my opinion, the only easy way to do a lot of parsing problems. Like, I'm not going to go over problem 16 because I really didn't like that problem, but that parsing is actually made pretty simple by just using a recursive function that mutates the tokens as it consumes them. So hopefully this general concept helps you more than just solving this problem. Yeah, so thank you all for watching.